Okay, today we're going to talk about the formulas once again that we've been going over, and we're also going to talk something about cavalieri principle, which is something that you may or you may not be familiar with. Now, look on this page here. I think we're on page 7 now, and it's the bottom half. And these are the things that we want to go over today. We want to explain the relationship between base area, height, and volume of prisms and pyramids. Just kind of talk about that a little more and explain the relationship between the volume formula for a cone and a pyramid, and estimate the real world objects using comparable geometric shapes, and talk about cavalieri principle and what it actually means. So let's get our notes ready, get our pencils ready. Oh, I'll choose purple, my favorite. Volume of a prism. Remember what we had to do to find the volume of a prism. Capital V stands for volume. And we needed the area of a base times the height. And remember, capital B means find the area of the base. It could be a rectangle, it could be a square, it could be a triangle, it could even be a circle. In the case of a cylinder, the volume equals the area of the base times the height, same as the prism. It's just that capital B is always going to be a circle, so it's pi r squared, that's your capital B, times your height. Then we went on to learn about the pyramid, cone, and sphere. Now, since the sides kind of cave in on a pyramid, it's kind of like a prism, except the sides come in and they become triangles, so the container won't hold quite as much. So the volume now, instead of just capital B times H, it's going to be 1/3 times B, capital B times H. Or what we can do, if you find this easier, find the area of the base, multiply times the height of the pyramid, and then divide that number by 3. After you enter this into your calculator, enter, then divide by 3. The volume of a cone is very similar to the volume of a pyramid. Looks like this: 1/3 the area of the base times the height. And the only difference is the cone always has a base that's a circle. So what we could say is pi r squared times the height, and then divide by 3. Okay, since we know the cone has a circular base, we can just substitute pi r squared for the capital B. Now, the volume of a sphere, or a ball shape, is completely different. It has its own formula that's very different. That formula involves multiplying times 4/3 times pi, and in this case, we take that radius and we cube it. Always make sure you have the radius, not the diameter. If you have a diameter, divide that number in half to get the radius. Remember, 2 radii equal 1 diameter. Okay, so let's think a little bit here what the relationship is between the volume formula for a prism and a cylinder. And it's kind of like what I was just talking about. The volume formula for a prism is the area of the base times the height. The volume formula for a cylinder is pi r squared times the height. And I say they're the same because pi r squared in the cylinder is actually capital B. Same thing. So the prism and the cylinder actually have the exact same formula. What is the relationship between the volume formula for the pyramid and the cone? Okay, the second day we did pyramids, cones, and spheres, if you remember. So when we did the pyramid, we said, well, we're bringing those sides in, so instead of just area of the base times the height, we have to take out some, and it turns out it's actually 1/3 the amount of the exact same size prism that would have that same base and that same height. Okay, and for the cone, the volume is pi r squared times the height and multiply times 1/3 or divide by 3. Well, since the cone always has a circular base, that's why we insert pi r squared, because this equals capital B. So the relationship between these two formulas are they are the same thing. It's just that we write in pi r squared because we already know that the cone has a circular base. Same thing up here with prism and cylinder. It is the same formula. It's just that the formula, we know the base is a circle, so we substituted in pi r squared instead of capital B. Just to kind of help you out so you don't forget that. Okay, now we're going to look a little bit. I'm trying to see in my book here where we are now. We are at the top, almost the top of page 8. And we're going to look a little bit further into what happens here. What is the shape of the base? Okay, these are CD cases. I'm going to guess they are rectangles. Okay, and if I sketch it on a smaller scale, it looks a little bit longer going that way. I'll say it's a rectangle. What shape would the cross section be? Well, the cross section, which has to be parallel to the base, is going to be identical to the base. So I'll write same as base. Is the shape of the cross section and the shape of the base the same? Yes. By definition, the cross section needs to be parallel to the base. If we consider the number of CDs, the height of this prism, estimate the volume. Well, since the volume is the area of the base times the height, let's see, how many do we have? Maybe 1, 2, 3, 4, 5, 6, 7, 8, 9, maybe 10? If H equals 10, and our volume is going to be 10 for our height times whatever the area of the base is. Let's say a CD case might be, I'm just approximating 4 by 5 inches. So I could say capital B equals 20 inches. So my volume, when I substitute the 20 in for B, my volume is going to be 10 times 20, which equals 200, and these would be inches cubed. Okay, well, they're not really inches cubed because the volume, these little CD things are not an inch tall, are they? So we'd have to say 200, but I don't know really what we're comparing here. Maybe these are a centimeter tall. Maybe I could make this 40 centimeters by 50 centimeters. Then that might make more sense. Let me just erase this down here. And I'm going to change that because 40 by 50, well, now I'm talking about 40 times 50. It's 4 times 50 is 200. So 40 times 50 must be 2,000. Okay, so now I would have, and I'm talking about centimeters. I'm going to make these smaller. So the base would be centimeters squared. So I'm going to take 10 times 2,000 to get how many square centimeters I have. So that would be 20,000 centimeters cubed. I think that makes more sense to measure this in centimeters. Okay, just kind of an idea, just kind of an estimation there. Okay, let's look at this picture. Here we have a stack of nickels, and I'm thinking, what is the shape of the base? Well, it's a circle. And what is the shape of the cross section? Say I cut right through here. It's also a circle because my cross section needs to be parallel to the base. Is the shape of the cross section and the shape of the base the same? Yes, same as the CDs. If we consider the number of cases, this should be coins, the height of this prism cylinder, can we estimate the volume? So let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay, I'm going to say approximately 20 because you know very well I cannot see that close enough. So I'm going to say it's approximately 20 centimeters tall. 20, those would be millimeters. Let's call them millimeters because it's awfully small there. Okay, so if I was going to measure in millimeters, let's see, I'm looking at my ruler now to see how many little millimeters would a coin's radius be, and it might be like, maybe 10 millimeters. I'm thinking the radius might be about 10 millimeters. So if my height is approximately 20 millimeters, or 20 coins, and the radius on my circle has 10 millimeters, then I'm going to say the area of my base is 10 squared times pi, or 100 pi. So my volume is going to be the area of my base, 100 pi, times 20. So since 2 times 100 is 200, 20 times 100 must be 2,000 pi. And when I put that in my calculator, let's see if I can find it. I'm going to put 2,000 times pi in my calculator, and I get an approximation of 6,283 in 1900ths. I had to round that last one. And we said these are millimeters cubed. Okay, just kind of an estimation there. Now let's skip down to the bottom of page 9. The top of page 9 I'm going to have you work on your own. Okay, we're going to talk a little bit more, but then I want to talk a little bit about Cavalieri's principle here, and then I'll have you go back and do page 9. Cavalieri's principle says if you have two figures that have parallel bases, so one cylinder is going this way, straight up and down, and one is kind of on a slant, but this one has a height of 9 centimeters and a radius of 5 centimeters on its base. Cavalieri's principle says if they have the same height and the area of the base is the same, then their volumes are going to be equal to each other. It kind of makes sense, even though this one looks like a little slanted here. The area of its base is 25 pi. The height is 9. So when we take the area of the base times the height, we're going to get 225 pi, and that's going to be centimeters cubed. Okay, because 9 quarters is $2.25, so that's how I was able to multiply 25 times 9. Now when I go over here to the one that's standing straight up, the area of the base is 25 pi. The height is 9. Therefore, its volume is 225 pi centimeters cubed. Okay, so Cavalieri's principle says if two figures have parallel bases and they are equal and they have the same height, then their volume is the same. So what I want you to do is to go back and look at the problems, the pictures, the CD cases, and the coins above on page 9 and answer those questions, and then go on to page 10 and answer the 4 questions that go with each of the 2 diagrams. Okay, have a good weekend, everyone.